We should start, right? At 4. Maybe I'll wait for one more minute.
The last one started kind of late. I don't know why. The last session started kind of late. I don't know why.
So like a few minutes. It's fine. I think we'll be fine. Right? You are the first speaker.
Yes, I think so. You can start. I have
Yeah, let's maybe wait for 2 minutes more because yeah. I think, yeah.
Has Chirac left? Okay.
He looks so sad.
No, I'm okay. I think he's flying to Aarhus, so I'll catch him next time.
Yeah.
So he's flying again back. He cannot.
If you want, you have this printer.
He cannot escape.
Oh, no.
Yeah, the last session is expected to be. Oh no, somewhere they're ringing a bell. Yeah, let's wait for a minute. Right. For some reason. Last moment chair. Last moment chair. I hope so. Okay, let's start. Welcome to the last session of the conference. Thanks for all of those of you who are still here. So the first talk is testing conditional mutual information. Yeah, thank you.
Yeah, thank you very much. So our work is titled Testing Conditional Mutual Information, and it's joint work together with Sayantan, who's also here, and Marco. First, about our problem setting. So we are interested in the case where we get IID samples of a discrete distribution over multiple variables, and we are interested in testing correlations between these variables. So the easiest problem one might ask is, given two variables, say A and C, are there any correlations between them or not? And if not, then obviously the shared distribution is simply a product distribution. We are interested in a slightly more general case, where we also have a conditioning system, which we call B, and we kind of ask whether A and C are conditionally independent given B. And kind of the intuition is that there might be correlations between A and C, but they can be fully explained by B, such that there's no direct link of causation between A and C. And it turns out that if this is indeed the case, then the distribution also has a very specific form. Now, to phrase this as a testing problem, we will need a decision gap, and we define this in terms of the conditional mutual information, which is nothing else than the KL divergence between the original distribution and the conditionally independent variant of it, as I defined it before, and I will refer to this as the reference distribution in the following. And if you're just interested in the independence case, then of course the B system is simply trivial. Now, of course, you could consider order distance measures instead of KL. And one thing which has been studied before and which we will see later is the case where we have the L1 distance instead of KL. And the testing problem we are interested in is the following. So we are given IID sample access to a tripartite distribution and the guarantee that it's either conditionally independent or gapped away from it. And we want to distinguish with high probability which of the two cases holds. And more precisely, we want to know what is the minimal amount of samples as a function of the sizes of the different parameters and this epsilon, which are needed in order to solve this decision problem. To quickly come to our results, so hold on. This is the sample complexity we come up with. Obviously, I will not go into details into the different terms, but it's, at least to me, quite impressive that we have like these 5 different cases, which looks very complicated considering how simple the problem seems to be. But we actually do have evidence that this structure is tight. And then along the way, we of course also solved the special case where the conditioning system is trivial for mutual information testing. And here we actually derive matching lower bounds up to logarithmic factors. To give a top-level overview of our approach, so the basic idea is that we reduce the problem to equivalence testing. For those unfamiliar, in equivalence testing, you have sample access to 2 unknown distributions, and you just want to know whether they are the same or gapped away from each other. And in our case, we of course only have sample access to the original one. So the first task will be to simulate samples from that reference distribution. We also want to be very efficient with the equivalence testing. And since our reference distribution have an additional structure, we of course hope that we can be more efficient than just using general equivalence testing. And one thing I will not go into detail about is that we phrased our problem in KL divergence, but it's actually easy to reduce it to squared Hellinger. And so I will just discuss the squared Hellinger one in the following. And one thing I want to go into a bit more detail about is how you can actually perform general equivalence testing in the squared Hellinger distance following an approach by Diakon-Nicolas and Kane. So this is done in 2 steps. In a first step, you take one of the 2 distributions and you approximately learn it such that you can bucket the indices of the distribution. So you split your distributions into pieces of similar weight such that within each bucket, all indices have the same weight up to a constant factor, except for one last bucket where you have all the small weights. And then in a second step, you perform piecewise equivalence testing in the L2 distance. And this bucketing is kind of necessary because otherwise switching between squared Hellinger and L2 would be very costly. But since you just have a logarithmic number of buckets, this piecewise testing is not too expensive. So to start with our contributions, I want to go over mutual information testing because this already shows all the basic ideas. As was mentioned before, we want to test whether the distribution is a product distribution or gapped away from it. And the first thing we need to do equivalence testing is to sample from this product distribution. This, however, is very straightforward. You just take 2 samples from the original one and you mix them like this, and then it turns out that these resulting samples have exactly the statistics we want. Coming to the equivalence testing, here the question is, can we make use of the product structure? And the answer is yes. So on the slide before, I showed you how one can bucket this distribution. And what we can do now is that we just bucket both of the marginals individually and then plug the thing together. So this is what I tried to visualize here. Each of these kind of buckets on these 2-dimensional grids depends to one test in L2 distance which you have to do, and the sample complexity is dominated by these red buckets. And this is the sample complexity we achieve, and we also show that it is tight. Now coming to the conditional case, here the intuition might be that we can just do the same thing, but now in 3 dimensions, right? So in general distributions, you just have your 1-dimensional bucketing. In this 2-dimensional case for independence testing, we had 2 dimensions. And now when we also have a conditioning system, we just add 1 more dimension. And this intuition almost works, except for an additional regime we need here, which we labeled the small regime. And the reason for this additional case distinction is that sampling from this reference distribution in the conditionally independent case becomes more tricky. So let me quickly illustrate why this is more tricky. To make this most intuitive, we first assume a slightly idealized setting where we have sample access not only to the original full distribution, but also to an oracle where you get to condition on B. And then you could just request 1 general sample, and then a second one with the same B coordinate as the one you've already observed, and again mix them as we've done before, and it turns out that the statistics of the sampling procedure are exactly the ones we want. Now, of course, we do not have access to this oracle, so we need to simulate it. And in principle, this is not difficult. You could just take one large batch of samples, sorted by the B coordinates, and then to request a specific sample from a specific B coordinate, you just go to that bucket and take a sample. The bottleneck of this is that, of course, you need to always guarantee that these queues are not empty, and if the probability PB to see a certain B is very small, this can get very costly. And for this reason, we only apply this approach in some regime. And in the other regime, we follow a different approach. So there's a cutoff, depending on PB. Above, we do exactly what I just outlined. And this is what you saw on the slide before, this three-dimensional bucketing. But there's a small regime where we have to do something different. And there we perform what we call a collision-based sampling. So you just witness your stream of samples, and as soon as you see two with the same B coordinate, you combine them again in the same manner. Now, I'm not going into more detail about this, but it's important to note that kind of on a very top level, it might seem that both of these approaches are more or less the same, because in both we combine the samples in the same manner. But it's very important that in this collision-based approach, since this is kind of a two-stage process, we introduce correlations and a bias between the samples, right? So the original samples we got were IID, but after our sampling, they are correlated and biased. And this makes, of course, the resulting analysis in the equivalence testing more tricky, and we introduce a new estimator for equivalence testing in L2 to help us with that. Now, to come back to our results, again, I don't think there's any point in going into the detail of these terms. I just marked the two different regimes, and now we can come back to this question of whether this complicated structure is indeed necessary or just a result of the specific approach we took. And here I want to mention the prior work, which studied the same problem with respect to the L1 distance. And as you can see, they also get a very complicated structure. And the interesting thing is that they kind of follow a different approach in which they reduce the problem to estimating the value of a polynomial. And in fact, in some regimes, their sample complexity exactly coincides with ours. And this might be a first indicator that this is indeed tight. So let me go into slightly more detail here. What kind of lower bounds do we have? So the first thing is that we show certain lower bounds. This is here in blue, so this term is just tight. And this also gives the tight lower bounds for the mutual information testing. And then this prior work by Canon and others, they also showed some lower bounds, which happen to carry over to ours. And while there are still some terms which have not been fully determined now, we can say that this basic structure we see here with these 5 different cases and the nested case distinction is indeed necessary. Yeah, so this already brings me to the conclusion. We studied the problem of testing for conditional mutual information. This is the sample complexity we arrived at, and we also have some lower bounds which indicate that this structure is mostly tight. And I think it's particularly interesting that it also shows that this sampling in the small regime, where we have the bias and correlation, is in principle optimal with respect to the scaling in certain parameters. Yeah, thank you very much for joining on Friday afternoon.
Thank you. Let's thank the speaker. Yeah, so we have time for a few short questions. Please, anyone in the audience? Okay, I have a question. I think people are thinking. So you said that there is a simple reduction from KL because question to the Hellinger. So you have some built-in assumption, right, on the ratios of densities, or like why are they equivalent in your case?
The trick is that, like, since the two distributions are not arbitrary, you can make a simple pre-processing which introduces minimal eigenvalues. And then you just get a log factor when you go from one to the other.
So there is a log factor hidden in the theta somewhere?
Yeah, that's what the tilde means.
Okay, like, okay. So there are like log factors of the ratios of okay.
Exactly, like the smallest eigenvalue. Mm-hmm. And then, of course, like for the testing, you also get a lot of log factors.
Yeah, okay. Yeah, thank you. Any questions? in the audience? Okay, let's thank the speaker again. So you're number 3, I think. So, okay. Yeah, the next talk is testing juntas and junta subclasses with relative error.
Hi everyone, so I'm William, and I'm going to be talking about joint work with my three advisors at Columbia University, and this is on testing juntas and junta subclasses in a new model of property testing called the relative error model. So in property testing, you have some unknown function f, and you want to see, does it have the property you're interested in, or is it far from the property under some notion of distance? In this talk, we're going to focus on Boolean functions over the hypercube, and the goal of this problem is also to only look at a very small fraction of f. You don't want to query the whole hypercube. And this problem has lots of connections to learning theory, and in particular, the algorithm I'm going to talk about is related to learning. So since it's a new model, I'm kind of going to ramble about property testing a little bit. So in the standard model, you can access f by asking membership queries. So given x, what is f of x? And the distance between f to a property is the minimum distance between f and any function in the class, where the distance between f and g is the symmetric difference between the two functions divided by the domain size. So in this talk, I'm always going to use like blue blobs for f and red blobs for g. And so here you should think about how much do they overlap divided by 2 to the n. So what happens in this model when you're trying to test very sparse functions? So think about a function where what you're really interested in is like the ones of the function, but there's very, very few of them. So imagine like the total number of 1 is like 2 to the n over 2. Then you're kind of running into two issues. The definition of distance from between f and the property is basically the same as the distance between the zero function and the property. And another issue is that if you only allow your algorithm to make few queries to the hypercube, it's going to query like a bunch of places, and most likely they're all going to be answered by 0. And so you can't really do anything meaningful. So in recent work at SODA, they introduced a new model called the relative error model, which is based on a new notion of distance, which is more tailored to these sparse functions. So the relative distance between two functions is still the symmetric difference, but now you divide by the number of ones of f. So this is always going to be bigger than the standard notion of distance. And when f is sparse, this is going to be a lot bigger, which is a good thing. And now that kind of defines you a new problem, which is, does f have the property, or is it relative error far from the property? And so how should you be able to access f? So obviously, you should still have membership queries. But if you only give me membership queries, you still run into the problem that to even find the one of the function, you would need a stupidly large amount of queries. So to remediate to this issue, you can also get uniformly random satisfying assignments of the function. So now you have two ways of accessing f. So that's a new model. How would it compare to like the standard model? So roughly speaking, it's just like strictly harder. So here, Q standard is the cost of the best tester in the standard model, so only counting number of queries. And QL is the cost of the best tester in the relative error model, so counting both queries and samples. So what they showed in this original work is that there's some property that's like super easy in the standard model, but like stupidly hard with relative error. And they also showed that generally speaking, when you have a tester in the relative error model, you can turn it with a small blow up into a tester in the standard model. And for people who are more familiar with property testing, you might wonder how this compares to distribution-free property testing. So it turns out that these two models are actually incomparable. So in parallel work to these, we showed conjunctions are easy for relative error, but they're known to be hard for distribution-free. And you can also cook up some artificial property that would be very easy distribution-free, but really hard for relative error. And that was all about the model, and so now I can talk about our result. So the first thing we studied was testing k juntas. So a function is a k junta if it only depends on k variables. And as you can tell by the very long list of reference, it's super well studied in property testing. And every time the goal is to get an algorithm whose complexity only depends on k and epsilon and not n. And we also studied subclasses of k juntas, which are closed under permutation. So here you should really think about like a size k decision tree. So the bounds we get for k junta is like basically k over epsilon times some log factors. And if pk is a subclass of k juntas, what we're really going to be interested in is this class pk star, which is the function in the class which only depend on the first k variables. So pk star is going to be much smaller than pk because you don't have k choose n variables to work with. And so the size of pk star is always some function of k. And so in this case, we basically get k log the size of pk star over epsilon, and that's always going to be a function of k, no dependency of n, which is a good thing. So now I'm going to talk about like this second result and how it works. So this is inspired from the work of Nader Bashudi, which was interested in the same problem, but in the standard and distribution-free setting. And the idea is to check, is there some permutation of the variable such that my function f is close to some function g in pk star? The big issue is you can't explicitly find what variables f depends on because you would need omega log n queries, and that's too expensive. So the usual trick is to work with blocks. So at the beginning, the algorithm is just going to pick like a uniformly random partition of the variables into k-square blocks, roughly. And then you try to find which blocks the function depends on, which means you have some evidence that the block contains a variable that f depends on. So here you have 2 points. They agree on all the coordinates in the first 4 block, but not in the 5th one. And somehow f on the first point is 1, f on the second point is 0. So here you could tell that the function depends on some variable in B5. And now we finally get to learning. So now the idea is that you're only going to run a very naive learning algorithm. So your set of candidates is just going to be pk star, the functions in the class that only depend on the first k variables. Then you do a bunch of samples from f, and you have to remap them using the block, and that's like the annoying technical part. And then all the candidates you're left with look like this. So they are red blobs that basically cover all of f. But at this point, you're not really done because you have some good red blobs and you have some really bad red blobs. So the blob on the left is very big compared to the blue blob, and so that would be big relative distance, whereas the blob on the right is really good because the 2 blobs basically overlap perfectly. So now you run into this issue that you have lots of candidates left, but you don't know if there's a good one. And you can't really afford looking at all of them. So it turns out the best thing to do is actually to pick the candidate that has the least number of ones, because that's somehow going to minimize the relative distance, even if it's not the best. And so you pick this candidate, and then you can, roughly speaking, generate uniformly random satisfying assignment from that candidate, and you can check, is that candidate a subset of f? If yes, then you're like in the first case where like g and f are like 2 blobs that overlap really well, so you can accept because f is close in relative error to some function in the class. And otherwise you reject because your red blob was way too big, and so the relative distance is high. And to test runtas, well, it turns out you don't even need this learning step. You can do something much simpler, but it's like a little less fun to present. And you know, in terms of open question, this whole algorithm is related to like relative error learning, but it's very, very slow. So more generally, like given a class of function, can you do like efficient relative error learning, which means can you find some function g that's going to be close to f in relative distance? And here you can think about 2 models, so only using samples from f. There's been some work on that from like years ago, or using both samples and queries. And that's all. Thank you.
Yep, let's thank the speaker. Yeah, so any questions in the audience? Okay, maybe I also have a question here. So you mentioned that this relative error on one of your first slides is somewhat, like the upper bound is somewhat different, like it's multiplicative with the size, while the standard model is additive. So is it like kind of should it be like this, or is there a way to reduce one to another? Or?
So Nader Bashudi gets the same like multiplicative thing in the distribution-free setting. And the reason is that whenever you draw a sample, you have to remap it in this setting. And so that's why like for each sample, you have like this k factor, because you need k queries to remap a sample. Whereas distribution-free, you don't have, like standard setting, you don't have to remap them. So it's just, like for each sample, it costs you like no queries.
Okay, but it's for this specific algorithm, so maybe there is something around it.
That would be crazy, I think.
Okay, good to know. Okay, yeah, thank you. Let's thank the speaker again. If there are any questions, okay. Good. So I'm somewhat familiar with the next paper. It's called Lower Bounds for Greedy Teaching Set Constructions. I think this is an Easter egg for testing session. I'm not sure how close it's to testing, but yeah, please, Spencer.
Thanks. Yeah, so we're going to be talking about teaching sets. This is work with amazing collaborators, Trog and Nikita. So the main motivation, or at least ours, for studying this sort of question that we're going to talk about is kind of just trying to understand what sort of structure is really implied by a concept class having small VC dimension. So it sounds pretty vague, but there are some pretty concrete questions that kind of guide this. For example, one is the sample compression conjecture, and another one is the teaching set conjecture, also called the recursive teaching dimension conjecture. And we're going to be talking about the latter. And you can kind of think of this talk as like 50% an advertisement for a cool problem and 50% what not to do when you try to solve it. So if this is our goal, we should remember what VC dimension is. We kind of think of a concept class as a table where the columns are the domain and the rows are the concepts. And we say we shatter a subset of the domain if all 2 to the size of the subset possible labelings occur in the concept class. So the VC dimension is the size of the largest shattering set. But what is a teaching set? Maybe more interesting. We say that a subset of the domain teaches a particular concept if no other concept has the same labels on that subset. So for example, here, if we're trying to teach this concept with these 2 domain elements, this is a good teaching set because no other concept has 0 and then 1 on this subset. Cool, so this gives us everything we need to state the conjecture, which is that for every concept class with VC dimension D, that there's some concept with an O of D size teaching set. This, for example, been advertised in COLT 2015 as an open problem. So what do we know about this conjecture? One, it's stated the way it is for a reason. So there's not always, it's not always the case that all concepts have a small teaching set. A simple example is this like singleton concept class where we have a bunch of single ones in the concept and in addition to the all zeros. And there's no teaching set for the all zeros concept that's smaller than all of the domain. So you kind of need a large teaching set for this. But it's not a counterexample to the conjecture. Right? There's some concepts with small teaching sets. Like if I take a singleton and I show you the one, then I know I'm looking at that singleton. Okay, so it turns out the most progress on this problem can kind of be viewed through the lens of a greedy algorithm that builds a teaching set. So the way this algorithm works is you have some greediness parameter k, which is a positive integer. And while the concept class still has more than one concept inside it, what we'll do is we'll choose a subset T star of the domain of size k, along with the labeling of the elements in T star. And we'll choose the one that minimizes the number of concepts that are consistent with this subset labeling, as long as the set is still non-empty of the concepts that agree. And then you add T star to your teaching set, you restrict your concept class to the ones that agreed with that set, and you continue until you've narrowed it down to one concept. Walking through a simple example, if we have this concept class here, and I have k equals 1, what we're going to do is we're going to choose the point in the label that restricts the concept class the most. In this case, we set x1 to be 1, and this restricts us down to 2, and then we'll set x2 to be 0. This gets us down to 1, and we have a teaching set for this concept. Okay, so with that algorithm, you can imagine for various k getting different bounds on the number of rounds this takes to converge to one concept. So for k equals 1, there's a very simple bound of log the size of the concept class size. And this is just because at every step, we're going to be at least halving the concept class. But some pretty interesting stuff happens after that. So for k equals 2, there's a result that says you can do it in O of d to the 2 to the d log c rounds, so much better than this naive bound. And we even now know that if k is a large enough constant times d, that this finishes in O of d rounds. So since you got a teaching set that was k times the number of rounds, this gave you a O of d squared size teaching set, and this is the best that we know so far. So a very plausible seeming program would be that maybe you could study k being little O of d and try to really correctly analyze the number of rounds that this takes and try to resolve the conjecture this way. Maybe even when k equals O of 1, it would take O of d rounds and then the conjecture would be done. But the point of this work that we're going to be talking about is that actually this program doesn't work. So we're going to be providing some concept classes that kind of force this behavior. So in the case of k equals 1, you can force this log c dependence. And then when k is anywhere between 2 and even a small constant times d, we can force this log c dependence. So there's really this big difference in behavior between small constant times d versus large constant times d. And this kind of shows that maybe to solve the problem, you really need to think about these theta of d level interactions. For the talk, we're just going to talk about this omega of log c bound as kind of a warm-up, and then we'll be out of time. So the goal to try get this bound will be that for any positive integer n, we're going to create a concept class, f sub n, which is the union of n sets, c1 through cn. The VC dimension, we want it to be constant. We want the greedy teaching set on this concept class to be n, and we want n to be omega log of the concept class size. So as a spoiler, our plan is going to be that our concepts will be very carefully chosen rectangles in the plane, so VC dimension will be constant. And we want that after one round of the greedy, the concepts we're left with is exactly the union of C1 through Cn minus 1. So after n steps of this, then the teaching set will be size n. And the size of our concept class will be like 2 to the theta of n, so we have the right dependence on n and the log of the concept class size that we want. Cool, so now I'm just showing you the concept class. It's a lot, but we can walk through what's really happening here. So we have a bunch of points. Those are our domain. And it comprises of the union of a bunch of sets v1 through vn. Each vi comprises of a center point, zi, in addition to wi points extending directly above it, and wi points going directly below it, where wi is like 2 to the 10i. And then we choose some rectangles carefully. So we have a set of rectangles, c sub I up, comma 1, which just contains like z1, all of the points, or zi, all the points directly above zi, and some possibly empty prefix of the ones below. So the rightmost red rectangle is one such. And then we'll also have c sub I up 2, which is like the same set, except you extend it leftwards to include all of v1 through vi minus 1. And you could similarly have these like ci downs, which include all the ones below zi and some prefix of the ones above. Cool, so this is our entire concept class. And it has VC dimension O of 1, right, because it's just a bunch of rectangles. The size, if we kind of think about it for a second, is the size we want. And then the final nuance thing is just showing that this is going to, after one step of the greedy algorithm, leave us with C1 through Ci minus 1. So if you think about what the greedy algorithm is doing, it's choosing the most biased point. Like it's choosing the point in the labeling that restricts the concept class size the most. So if you like wrote down for each domain element how many times it's 0 and how many times it's 1, it's choosing the most biased one, like it chooses one that's overwhelmingly 1. And exactly what we're going to prove is that zi is the most biased point. It's overwhelmingly 1, so the greedy is going to set it to 0. And if you could show that, then you'd notice that all of the rectangles in C sub I have zi as 1, and all the other ones have zi as 0, so we'll be exactly left with C1 through Ci minus 1. So roughly the observations of how this go is you would notice that we chose like this class so that Ci is like the majority, like the vast majority of our concepts, and that Zi is 1 in all of these, so it's 1 for a strong majority of our concepts. And then we just need to show that it's more biased than the others. So for x in like v1 through vi minus 1, it's going to be like 0 for half of Ci, because it's going to be 0 in all the red ones. And it's going to be 1 for the other half, so it's going to be because all the blue ones. So it's pretty unbiased. And for the remaining x that are like in vi, but not zi, it's going to be like 1 for at least half, because if it's like above zi, for example, it's going to be in all these up rectangles. But it's also going to be 1 strictly less than zi. And then, like, if you think for a second and put these all together, this is enough to show that you're going to choose zi and set it to 0, since it's the most biased now. So maybe that was a little fast, but wrapping up, what did we learn? Well, we learned that log C bound, but maybe the more consequential bound is this, like when k is up to a small constant times d. But it's a little more complex, but the plan ended up being quite similar. Like we kind of designed the concept class in a way to force you to choose exactly what we want you to. But of course, the teaching set conjecture is still very open. But maybe we now know that we should be like, we really need to understand what's happening at these like theta of d order interactions. We can't like just look at these really much smaller order interactions. Thanks.
Let's thank the speaker. Yeah, so any questions in the audience? I know many questions for this paper, so. Okay, I think it will be hard to answer, like, how should we solve the conjecture, right?
Yeah, I wish we could have.
Oh, there is a question. Okay, Omar, please.
Hi. So if I understand correctly, so the lower bound rules out, so I believe the paper that showed the upper bound of order d squared has a sort of suggestion of how to improve their upper bound, where they have a recurrence relation, and that if you improve the recurrence relation, you would get a. So, is it correct that your result basically shows that this is not possible?
Yeah, so this is a great question, and it's one that I was like trying to not explicitly say because maybe they're a little vague in their wording, so if they want to say that it doesn't rule it out, they could. But okay, basically the paper says that the teaching set of a something of VC dimension D, like T of D is less than or equal to T of D minus 1 plus O of 1. So like, okay, if the teaching dimension is always O of D, then this like recurrence relation is technically always true. But like, I think the spirit of the comment was that you could like keep choosing these K of size O of 1, and after D rounds, it would finish. And if that's the spirit of the comment, then yeah, this kind of rules it out, yeah.
Okay, cool, thanks.
Any other questions? Okay, let's thank the speaker again. So the next talk is called Computing High-Dimensional Confidence Sets for Arbitrary Distributions. Yeah, thank you.
Hi, I'm Vaidehi. I'm a student at Northwestern University. And today I'll be telling you about computing high-dimensional confidence sets, which is joint work with my colleagues who are all in the Chicago area. Chao is at the University of Chicago, Liren's at Toyota Technological Institute, and Arvindan, who's my advisor, is at Northwestern University. So what do we want to do with a high-dimensional confidence set? The goal is to find a high-density region of an arbitrary distribution. So kind of formally, given samples drawn IID from some unknown distribution D over a little d dimensional space, and a target coverage rate delta that's given to us as an input, we'd like to fit the smallest volume confidence set such that it captures a delta probability mass over this unknown D. And the fact that we're trying to find something that's explicitly a small volume confidence set, we're going to refer to as volume optimality. So you should think of this as kind of being an optimization problem where we have a coverage constraint and we're minimizing volume. You can think of delta as being a fixed constant for the purpose of this talk. Maybe we want something that captures 90% of the distribution, but it doesn't necessarily need to be something that's bigger than 1/2. So this is a central problem in statistics, just to give you some ideas of where something like this might show up. It shows up in problems like conformal prediction, which is about generating confidence sets. It shows up in estimating density level sets, because the smallest volume set that actually achieves a certain coverage is a density level set. Mode estimation, if you think of like, I only want to cover 1% of the distribution, then maybe that set that covers it gives you an indication of the mode. Support estimation, if you want to cover like 99% of your distribution, then maybe that tells you where the support is. And robust estimation, which I'll tell you more about, and more. Okay, so the trouble with what I've told you so far is that it's impossible. So imagine you're given samples that look like this. It's impossible for you to tell me whether the distribution that they were drawn from looks like this, which is uniform over this blue region, or looks like this, which is uniform over the green region. And because you can't distinguish between these two distributions, you can't really tell me whether the best confidence set has to be big or it has to be small. And so this means that you're forced to either lose in coverage or in volume, even in 1 dimension. Here I've drawn it in 2 dimensions, but this is just a statistical issue, not one with dimensionality. So this brings us to a restricted form of volume optimality. So how can we restrict this problem? One strategy would be to restrict the class of distributions that we can do this over. So one example is a strategy that goes through density estimation, where essentially you take your samples from your distribution, you fit an estimator for the density, and then you take a level set of the density, and that has to be the densest set if your density estimation is pretty good. And this works for nicely behaved distributions in 1 dimension. But density estimation becomes statistically intractable in high dimensions. So we shouldn't expect this strategy to work in the high dimensional setting. So a different strategy would be to restrict the class of confidence sets that we're going to compete against. So maybe I don't care about getting an arbitrarily complicated confidence set that gets the exact coverage with the exact minimum volume. Instead, really what I want is, if it's in R, I want a confidence interval. If it's in RD, maybe I want a ball. And that's like a more useful notion of confidence set for me to work with. And one thing that's nice about these two examples I just told you is that there are set families of bounded VC dimension, which means they exhibit uniform convergence. So, as we've all seen in the previous talks, you take as many of these sets as you want, and once you draw polynomially many samples, you can kind of estimate the coverage of all of these sets simultaneously. So at least it should be statistically tractable to find the minimum volume ball that covers some set fraction of your distribution. And so our updated goal is to compete with the best set in some family. Okay, so here's what we're going to do. We're going to focus on the set of Euclidean balls in RD. And our updated problem is let B star be some unknown minimum volume ball that achieves coverage delta over some unknown distribution D. And now given samples from D, you want to find a set S hat that also achieves coverage delta over D, such that the volume of S hat is comparable to the volume of B star. And it's also natural in this problem, since it's high-dimensional, to compare radii, where the radius of the ball, of course, is the volume to 1 over D. And S hat might not be a ball. It's allowed to be any set. But we'll take that volume to the 1 over D also to do an apples-to-apples comparison. OK, so what does this look like? We have some samples drawn from D, or this is what the distribution D kind of looks like. And there's some unknown ball B star that is the minimum volume ball that achieves our target coverage. And what we want to do is output some set S hat that has coverage at least delta, which is what we wanted, and volume that's not too much larger than B star. And S hat, as I mentioned, doesn't necessarily need to be a ball itself. We've defined this similar to pack learning. And so if S hat actually was a ball, we would call that proper learning. And the arbitrary nature of D here makes this a worst case problem rather than an average case problem. And the reason is that, at some level, you have to be able to solve this problem over arbitrary adversarially generated point sets, because I could kind of embed this as a distribution by taking the uniform distribution, and I've made no assumptions over the distributions over which I want this to work. OK, so this brings us to the question, this so far so good, but how do you even compute such an S hat in polynomial time? This seems like a high-dimensional problem. What will we do? And if we had a bunch of samples, we could find the minimum volume ball that encloses all samples in polynomial time through a semi-definite program. But capturing a delta fraction is more challenging, and we're going to hope to do this through by proving a volume approximation guarantee. OK, so the way we tackle this problem is by drawing an analogy to robust estimation. So our goal is to compete with B star, which is the optimal ball that covers a delta fraction of D. And robust estimation in 30 seconds is a set of problems that looks kind of like this. You're given samples from a distribution where a delta fraction is the good inlier distribution, and a 1 minus delta fraction is the bad outlier distribution that was generated by some adversary to trick you. And you want to estimate the properties of the good inlier distribution while ignoring the bad outlier distribution, the samples that came from the bad outlier distribution. And so why does this look like our problem? Well, OK, maybe these points are all drawn from our distribution D. We can imagine that somehow in the back of our minds it's split up into the good inlier distribution, which lies inside the optimal ball, and the bad outlier distribution that lies outside the optimal ball. And we would like to estimate the center of this ball, which is the center of the good inlier distribution. And the center is the point that minimizes the maximum distance to the points. If we could do this, this would give the center of B star. And then it turns out it's pretty easy to guess the radius by just trying things on our samples, so that's not so much of an issue. The main thing is guessing the center. And maybe hopefully this gives you kind of a sense that these problems are related not just in this reduction, but any method that actually produces small confidence sets from distribution kind of has to be robust to outliers. It needs to know which points are really just not worth covering. And so this connection between confidence sets and robust estimation is kind of inherent. That's something we're trying to convince you of in this work. Okay, so great. Can we robustly estimate the center? Well, not really. In RD, the center only depends on d plus 1 points, so it's not robustly estimable. So you can't even, and basically here's a picture. Imagine these are the samples you saw, and this is B star. Well, B star depends on these three very specific points that describe where it is, and the rest of the distribution doesn't help you figure out where it is at all. So you shouldn't be able to robustly estimate this. And so to get a foothold in this problem, we're going to consider a relaxation where we're still going to compete with the best ball that covers a delta fraction of the points, but now we're only going to cover a delta minus gamma fraction for small coverage slack factor. So here I said earlier, think of it as like we're trying to cover 90% of the points. So I'm still going to compete with this blue ball that covers 90% of the points. But I'm going to let myself get away with only covering 89% of the points, and I'm going to be happy with this. And this coverage slack is pretty benign, we think, and it gives us a major foothold in the algorithmic problem. Because it turns out that once you allow for this slack, you can use the mean as a robust proxy for the center. And we have a lot of good techniques for robust mean estimation. So this is maybe the mean of the points inside the ball, and it's not necessarily anywhere near the center. But the point is we can robustly estimate it, and this gives us like a set that still captures most of the points in B star. And because we can estimate it better in some directions than others, based on the variance, the prediction set that will output is an ellipsoid. Okay. So we give a polynomial time algorithm that for a target coverage delta and coverage slack gamma, given some polynomial number of samples, we get a set that achieves the desired coverage, and the volume of the set that we output competes with the volume of the best ball times something that's exponential in d to the 1/2. So if you were to write this in the volume to the 1 over d, which is the like radii comparison, you get something that's like 1 plus 1 over root d. So it's like much less than like a 2-factor approximation in radius. And some interesting things combined, we actually get a hardness for approximating balls with balls. This is something you can see our paper if you want. So this actually gives us separation between the proper and improper learning versions of this task. Like we have to output an ellipsoid to get an approximation factor this good. We can use these ideas to compete against sets that are unions of balls. And there's a beyond worst case extension, but I'm out of time, so I'll get to the conclusion. We have many future directions, but you can come ask me later if you're interested.
Let's thank the speaker. Yeah, so we have time for 1-2 quick questions. Okay, I have a quick question. So you're saying that like you use ellipsoid to compete against balls, but let's move forward. If you compete with ellipsoids, will ellipsoids be enough, or you will boil down to the same problem?
That's a good question. I'm not sure. It seems like the problem of competing against ellipsoids to us seems harder because it captures this problem of robust subspace estimation. So essentially, the ellipsoid you're competing against might have volume 0, and this poses a challenge for us, the way we've defined this as a multiplicative factor. So we're not sure how exactly to tackle this problem, but maybe we could compete with ellipsoids using ellipsoids for the right notion of competing.
Okay, thank you. Any other questions? Okay, let's thank the speaker again. Yeah, so the next talk is called Testing Thresholds and Spectral Properties of High-Dimensional Random Toroidal Graphs via Edgeworth-style expansions. Yeah, floor is yours.
Yeah, so good afternoon. I'll be presenting our paper on random geometric graphs, which is joint work with Sam Baguli, Andreas Göbel, and Markus Papik. So let me start with some motivation and background. Why do we study random geometric graphs? Essentially, they model the quite natural phenomenon that a network forms based on some kind of underlying latent structure. Think, for example, of social networks where vertices have some kind of feature vector describing some kind of interest, and two vertices will be likely to be friends if they have similar vectors or similar interests in this case. Now, mathematically, we can model this quite generally by simply saying we have n vertices, and every vertex gets a random feature vector xv sampled from some distribution over a metric space. Then we say an edge uv will be added whenever the distance between these two vertices is below some threshold tau. Also, usually we only observe the graph while the feature vectors are hidden, and this gives rise to a sequence of interesting statistical tasks, all related to learning something about this hidden feature space given only the graph G. Examples include that have also been studied from a more practical side, recovering this latent structure, embedding a graph, and we can also think of clustering problems or community detection, and there's also this graph matching, which we also heard about yesterday. In this talk, however, we're going to take a step back and we'll ask the slightly more fundamental question of when it is even possible to detect whether a given graph has an underlying latent structure or not. So essentially what we're interested in is this testing problem here. Null hypothesis is we're given a pure noise graph, so an Erdős-Renyi graph, where edges are absolutely independent and all included with some probability p. Alternatively, we're given a random geometric graph over a metric space where the parameters are chosen such that this marginal edge probability is still p. So the expected number of edges will be the same. But the question is, can we still distinguish these two distributions? Reason why we study this is that understanding this problem allows us to learn something about this graph distribution, which will also allow us to potentially say something about these more advanced problems up there. So because of that, this testing problem actually has received some attention over the last decade, where most works have focused on the d-dimensional sphere under L2 norm. Here, it turns out that there's an interesting phase transition happening in the feasibility of this testing problem. So when d, the dimension of this underlying space, is large enough, then testing will become impossible, as you might imagine, since correlations will become very weak between edges. This is this blue, yellow, and red region in this phase diagram here. It states essentially that the total variation distance between these two distributions goes to 0. So there's no algorithm that can tell them apart. On the other hand, in this green region, so when the dimension is small enough, there is a simple test based on something called signed triangles, which essentially look at every triple of vertices and then measure how these edges correlate that form. So this is a stochastic version essentially of the triangle inequality we test for, which we expect to be more pronounced in a graph with underlying latent structure. As you can see, there's still some kind of open gap here. But at least in the case where p is a constant, we can tightly characterize the feasibility of this problem. However, these works all quite heavily build upon spherical symmetries and the fact that we can understand these graphs in terms of inner products, which breaks down when we go to other metric spaces or even just in different distance function that we might prefer to measure similarities between vectors. So the question arises whether we can hope to get similar results on different metric spaces, in particular for different distance functions. To get closer to answering this, we will switch to the d-dimensional torus instead of the sphere. So we will think of the torus in terms of the Cartesian product of d unit circles. And in this setting now, when we sample positions uniformly at random, we can actually use arbitrary distance functions to measure these distances, while asymptotically still getting this convergence to Erdős-Renyi as the dimension goes to infinity. Turns out on the sphere this is not true. When we use a different distance function, we essentially break the symmetry, which means that the limiting graph distribution will be different. You could still ask the question of whether you can distinguish the infinite dimensional and the finite dimensional version, but on the torus this problem is sort of more cleaner since we get this well-known Erdős-Renyi distribution. And it's also a more general model because now we have a free choice of a distance function. So that's what we aim to study. And there's only one previous work that has been looking at this from a testing perspective, which was published in last year's code by Guy Bressler and Kirill Bangachev, who looked at this problem for L-infinity distance. Turns out here you get actually quite different testing thresholds. However, the analysis is still quite limited to the specific case of infinity distance, and it is built upon the observation that an edge in this model is existent if and only if it exists in every single dimension. So only if in every dimension two vertices are close. Means that we get some kind of factorization, and all of our calculations will basically reduce to a single dimension, which makes things quite a lot easier. However, if we use a different distance function, for example, an LQ norm, where Q is now something different than infinity, this breaks down, and we sort of have to look at all of the dimensions at once, which makes it quite a lot more challenging. Also, we don't have an inner product space, so we cannot hope that the techniques from the sphere carry over easily. So that's the reason why prior to us this was very poorly understood, and there were only partial results known, in particular no tight testing thresholds, and it was not even known how well these signed triangles perform in the setting. We improve upon this by introducing a new technique for looking at signed subgraph counts based on these multivariate edgeworth expansions, or a modified version of that we introduce. So what we essentially look at is, given some pattern graph H, so some copy of a fixed graph H in our large random graph G, we look at this expected signed weight, which is essentially a product of random variables that alternate in sign, in Easy's case between +1/2 and -1/2, depending on whether a given edge in E is present or not. And the reason why this is interesting for our testing problem is that it quantifies some kind of dependence between edges. So if edges were independent, then this will always be 0. And if it's not 0, then edges are dependent, but we can use, or we can measure the distance this expected value has from 0 to say something about how correlated edges are, which is why it allows us to quantify this, or to characterize this testing problem. So what we concretely obtain as improved results for this RQ model on the torus are 3 things. So the first is that we can now tightly characterize how well signed triangles work, and more generally also signed cycle counts. We show that they have the same guarantees as on the sphere, and this now matches also the lower bound in the dense case. We also improve upon the information theoretic lower bounds. This is also based on looking at these signed subgraph weights when we choose suitable pattern graphs H. So we cannot only study concrete tests, but we can also characterize when testing is impossible. This improves upon the previous known results in the sparse case, and it now also matches the previously best known lower bounds for the sphere. Again, this holds on a more general class of metric spaces, which is our contribution. And finally, we can also analyze the spectrum of these graphs. So we get almost tight bounds on the spectral gap, and also explicit approximate eigenvectors associated to large eigenvalues. Here's another kind of a phase transition in the second largest eigenvalue that we can study, and we also get bounds for the case of infinity norm, which were previously not known, and which show that also spectrally these two regimes behave quite differently. So to say briefly a couple of words about how we achieved this, I mentioned already that we use these edgeworth expansions. We apply them essentially to a class of random vectors, which we call Z. And that Z will have a component for every edge in K, which we set equal to some kind of rescaled distance. Now we want to essentially look at the joint distribution of these components and quantify the dependencies. We achieve this by looking at the cumulant generating function, which is associated here. So we essentially use Fourier theoretic methods. We use essentially the Fourier transform, take the logarithm. This lets us end up with this cumulant generating function, which can be expressed as a power series here, where you end up with one k-tuple of natural numbers for every term. And this coefficient that you end up with for a given S is called the cumulant. The cumulants now allow us to understand this distribution, and we use a couple of observations to characterize dependencies. So what we do essentially is we split them into 2 classes. We have on the one hand pure cumulants, which are those where only one of the SIs is non-zero. So that means intuitively these only tell us something about the distribution of a single edge, and taking all of them together, inverting the Fourier transform and integrating would then give us exactly the same kind of graph distribution we would get in an Eder-Schwenny graph. So this is precisely what corresponds to independent edges, or like some kind of ground state, and all of the other cumulants are called mixed cumulants because they describe some kind of correlation between at least 2 edges, 2 or more edges. So they somehow give us perturbations from this ground state that we want to measure. The key observation now is that If H is a cycle or a chain, or if it only contains cycles or chains, then these cumulants have a very special structure that we can exploit. Essentially, many of them will be zero, especially low-order cumulants will be zero, and the lowest order cumulant, which is non-zero, is the one associated to the all-ones factor here, which intuitively tells us that this should be the one that tells us what the largest kind of deviation from this ground state is, such that it tells us the expected signed weight up to lower order terms. So this is the intuition. After a sequence of technical proofs, this turns out to be true. So to actually get back to the joint distribution of Z, we use these Edgeworth expansions. Turns out there is a general way to do this, which lets you end up with some kind of approximate density. The ground state here is Gaussian. For us, it turns out this is not the right way to do it because we want to have another ground state, so we basically introduce a new version of deriving them, correcting this ground state. Now we have this red term here, which after integrating exactly gives us an Nader-Shreni graph, plus a sequence of correction terms that capture dependencies and involve this first order non-zero mixed cumulant. Yeah, after integrating this, we get explicit upper and lower bounds on these expected signed weights, which is why we can improve both upon concrete tests and also lower bounds. This is essentially our main contribution, this technique, and it is not limited to the torus, but will also allow us to study these random graph distributions on other metric spaces, even though we cannot always expect the same results. But it quite generally generalizes to, or quite directly generalizes to other kinds of product spaces. It also has some kind of applicability to non-product spaces given technical conditions, and it is also applicable when the limit is actually not Nader-Shreni, but some other distribution. So our main contribution actually is this technique, which gives us a new view on these random geometric graph distributions on more general spaces. Yeah, with that, I've reached the end of my talk. There are a couple of interesting open questions that I'm still going to say one word about maybe. So one thing is that we could improve upon the signed weight for more general H, which would nicely give us something like a low degree hardness and potentially bridge the gap between upper and lower bounds in the sparse regime, which is still there. We can also use these spectral properties that we derived potentially for algorithmic applications like clustering problems or a robust version of this testing. And finally, we can look at what happens when we allow this distance parameter q to grow with n, because then there will be some kind of additional phase transition, since at some point it's going to behave like an L infinity norm. And yeah, with that, thanks for your attention.
Yeah, let's thank the speaker. Yeah, so maybe one quick question, if there is any in the audience. Okay, just a super high-level question. So you sometimes like people work with like simpler maybe models of random geometric graphs, like something generated by a sphere, right, or some simpler geometry, not the torus. Like, will this your new technique be applicable to this? You know, like you mentioned something about other geometries, right, where you can when you can use your techniques, but maybe there is something more classical where you can use the same. Do you know anything? Have you tried anything like this?
So the torus is some kind of classical space you can use for studying context. Random geometric graphs. This also happens. So we look at the high-dimensional case now. Mm-hmm. There are also people looking at random geometric graphs in low-dimensional spaces. There actually the torus is one of the classical examples you can use.
You also like the sphere, for example, sometimes people use. So it is also applicable there.
Under certain technical conditions, yes.
Okay.
It is. Yeah.
So yeah, I think if that's it, let's thank the speaker again. So we're almost there. Just 3 more talks. Yeah, so the next talk is approximating the total variation distance between spin systems. Yeah, please.
Hello, everyone. I'm Hong Yang from Nanjing University. Today, I will present my work approximating the total variation distance between the spin systems. This is joint work with Wei Ming and Ming Ji. So we focus on the problem of total variation distance. It is the definitive distance measured between probability distributions, and it is also called the TV distance or the DTV. It is a fundamental task in the theoretical field, and it's a core measure in areas such as machine learning, security, and statistics. The problem becomes challengeable when the sampling space omega is exponentially large. So for the most general case, for the circuit distribution, the high-end algorithm has shown that even to decide the TV distance is small or large is complete for static zero-knowledge model. So we need to focus on specific distributions, such as product distributions. For the product distribution, recent studies from Bhattacharya and Feng et al. Shows that the exact computation is sharply complete, but for approximation the TV distance, both the fully polynomial approximation for both deterministic and randomized exists. So in our work, we focus on the TV distance between spin systems. So for instance, the hardcore model and the easy model are two canonical spin systems in the statistical physics and the statistical science. So in the rest of the talk, we will only focus on the hardcore model, while the following results can also be applied to the easy model. For the hardcore model, we are given a graph G and the vertex activities lambda on it. The sampling space consists of all the independent sets from the graph, and for each independent set, the weight function is defined as the product of its lambda weight belongs to it. Formally, we are given a graph G and the two hardcore models specified by the two parameters, lambda mu and lambda nu. We need to calculate the TV distance with relative error approximation. In our problem setting, we are given sampling oracles and counting oracles. For sampling oracle, it returns a sample from the hardcore distribution, which is close to the distribution. And for the counting oracle, we will estimate the partition function with a relative error epsilon. And then we will define the marginal lower bound, which is natural to satisfy for the spin system. We call a distribution is B marginal lower bounded if for any vertex and any valid color, the local marginal probability of its color is strictly lower bounded by B. Then we are given our main result. That's for, we consider the B here to be a constant. Then for constant bounded, marginal bounded distributions to compute the TV distance can be approximated by calling n square over epsilon square times of the sampling oracle and O1 times of the counting oracle. This gives a polynomial time reduction from the TV distance approximation to the sampling and approximating counting problem. Previous results have shown that for any hardcore model, under the Unix condition, there exists a polynomial sampling and approximate counting algorithms, and we use those algorithms as oracles. Then we get the following query. That there exists a FBIES in time n cube over epsilon square for TV distance between two hardcore models, provided that if both the distributions satisfy the above Unix condition and have a constant marginal lower bound. Notably, even if the marginal lower bound is not a constant, the FPI also exists. And on the other hand, if both distributions are beyond the Unix condition, then we can prove that the problem itself is NP-hard. So we first introduced an algorithm for additive error approximation, which was solved by Bhattacharya. It shows that given two distributions, if we are given access to both distributions mu and nu, then the TV distance can be approximated with the epsilon additive error using 1 over epsilon square sampling oracle cost. The main idea is to deformate the TV distance by a random variable x here. And we can see that x is an unbiased estimator, and the variance of x is less than 1. So we can use the Monte Carlo method to sample x. There's a practical challenge to use this result in our work. It's that we cannot directly access the mu sigma and nu sigma. So to solve this, we just use the counting oracle to obtain the approximated partition function instead of the real one. And we prove that use the approximated partition function can only give an error, absolute error of O epsilon. So now we solve the problem with additive error, but our goal is to solve the relative error. We compare these two settings. We can see that if the TV distance is constantly large, then both problems are equivalent. But if the TV distance is small, maybe exponentially small, then the relative error version is much harder. So the core challenge is first how to decide if the TV distance is small or large, and then how to approximate the small TV distance with relative error. To solve the first challenge, we give the concept of the parameter distance. Recall that we are given a graph G and two parameters, lambda mu and lambda nu. Then the parameter distance is defined as the infinite norm of the lambda mu minus lambda nu. And we prove that if either the constant marginal bound or the unique condition, then the TV distance is lower bounded by the parameter distance multiplied by some constant c. It shows that the small TV distance implies the small parameter distance. Then we have an algorithm for small parameter distance by deforming the TV distance, and we use another random variable w here, and we will show that to estimate the TV distance, the task is reduced to estimate the formula along the last line. And note that the random variable w can be sampled through the sampling oracle from mu. So we have a straightforward method to estimate w by Monte Carlo. And surprisingly, this method exactly works. That is based on the small parameter distance. We prove that it implies the random variable has a very good property of concentration. The variance of w is bounded by the square of the TV distance. Then we will have an overview of our algorithm. We have two sub-algorithms, one for the large total variation distance and one for small one. And we define the parameter distance between two distributions. So we first check the parameter distance, then use this to adaptively choose to use which algorithm. For the large parameter distance, we will use the method of additive error approximation, and for the small parameter distance, we will use the property of concentration of a random variable w and use the Monte Carlo to sample it. Finally, for the open problems, first for the multi-spin system, so our work focuses on the two-spin system, but for Q coloring and pulse model, which belongs to the multi-spin system, we want to extend those results to them. And more generally, for the high-dimensional Markov random fields, we want to learn about how to compute the TV distance in the perspective of the computational complexity. And on the other hand, there are many other distances to measure the difference between distributions, such as the W1 distance, which is recently widely studied. So how to compute this distance is a problem. And I guess this problem is much more harder. That's all. Thank you, everyone.
Yep, let's thank the speaker. So, any questions in the audience? Oh, there is one. Thank you.
So you mentioned the problem is hard when the parameter is beyond the uniqueness threshold. So can you say more about that?
I mean, this? Yes, so we prove that if both distributions are beyond the unique condition, then we can reduce this problem to the counting problem, then to say that it is simply hard.
So what if one of them is?
Yes, this is, we don't know, but we guess it is hard, or it is also hard, but we have no proof for one beyond one under. and we guess it's also hard.
Okay, thank you.
Yeah. So let's thank the speaker again. Yeah, so the next talk is called Identifiability and Estimation in High-Dimensional Non-Parametric Latent Structure Models. Yeah, please, the floor is yours.
Hi everyone, I'm Yi Chen from Tsinghua University, and this is a joint work with my advisor Peng Kun Yang. And as you can see, it's not quite about a testing problem, but I hope you find it interesting. Okay. So we consider the data generated by populations with latent subgroups exhibiting a conditional independence condition, which means that given the latent group, the coordinates are independent to each other. So the data distribution is a mixture of product distribution. And our goal is to understand when such a model is identifiable and how to estimate it. So for the identifiability, we mean that given mu, can we uniquely recover the components mu kj and the weights pi k? Of course, we allow permutation. This is necessary for recover from the data, recover mu kj from the data, because we can only usually we can only sample from mu. A fundamental result is that the linear independence of each mu kj for j from 1 to d. This ensures the identifiability, and this is often assumed for algorithm papers. However, this condition is a little restrictive and fails in some simple special cases. I'll give you some examples. For the first example, we consider a conditional IID model. So if the mu k1 equals to mu kd equals to mu k for each k, so the mu k is linear independent, then the model does not satisfy the linear independence condition. And a more specific example is that the Bernoulli mixture model, which is of independent interest from the computer scientist. If mu k satisfy the Bernoulli distribution, then any three Bernoulli measures are dependent. So for m larger than 3, the condition fails. Despite this, both models are identifiable when d is larger than 2m minus 1 if the component distributions are pairwise distinct. This is a recent work. I believe the latter is the code paper last year. So let's have an easy observation. So if mu11 equals to mu m1, then the model becomes like the following. So the mu1, intuitively, the mu1 makes no contribution to identifiability, because if you know mu, then you know mu1, and the rest of them is not a part of it. So what we do is we define an index for each coordinates, j, if every subset of mu kj of size L is linearly independent. So it's a partly independent. The above case is L equals to 1. And when L equals to m means full linear independence as before. So we want to describe what happens between these two extremes. It turns out that between these extremes, the coordinates still make a contribution to the identifiability. So for a subset S of D, we define a total diversity of S, which is the minimum of M and a summation. And the reason we minus a cardinality of S is because, as we see before, L equals to 1 make no contributions. So we can guess maybe L minus 1 has a contribution. Okay, so our main result is that if there exists a partition S1, S2, S3 of D, such that the value in the left exceeds a threshold, then the mu is identifiable. And we also have a converse result. There exists a non-identifiable mu0 such that the left is smaller than 2m plus 1 for any partitions. Okay, I'll give you a corollary. Maybe this is more direct. So we say if the jth variable is separable if mu1j to mu_mj are pairwise distinct. In that way, it is equal to the index we defined before, L equals 2. Okay, so for the model, let n mu be the number of separable variables. If n mu is larger than 2m minus 1, then the n mu is identifiable. So this clearly explains the identifiability condition. D is larger than 2m minus 1 in the previous papers, and for a more general non-parametric setting. So let's move to the next problem about the estimation. Once the identifiability is established, the next question is how do we estimate the components from data? So for simplicity, we assume a density model from here. We just, before we use the notation of mu, and now we use the notation of f. Okay, so we split the problem into two parts. The first part is the sample complexity of the model, which means how we, statistically, how well we can do to estimate f. And how the second part is how the error of the model propagates to the parameters. So first is a sample complexity result. I'm not going into details about it. It's a classical method. We first prove that if all fkj's are Holder smooth, then the sample complexity scales only polynomially with the dimension d and the number of components m. So in theory, we have a good estimator of f from the random sample. So we then introduce a perturbation result under a mild incoherence condition. So we require for each j and k non-equal to k prime, fkj and fk prime has a small angle. Okay, this is a stronger condition than the identifiability pairwise distinct condition we mentioned before, because we need a quantitative result, so it is not unexpected. So our perturbation result is saying that under incoherence, when d is larger than 2m minus 1 to ensure the identifiability, if a proper estimator f hat, which means it has the same structure as the model, satisfies f and f hat are close to each other, then also the mixing proportions pi k and the component densities fkj is close to each other as well. Of course, after permutation. I'm sorry, there may be a typo of the mixing proportion. It needs a sigma k as well. Okay. Okay. Last, we have an algorithm to actually do that. I'm not going into details of this. The algorithm is based on a tensor topic algorithm named simultaneously diagonalization or Genrich algorithm. I'm not going into details, just mention the correctness of our algorithm. So suppose d is larger than 2m minus 1 under the incoherence condition for the true model. We have any for any estimator that's close to the true model, true density, the error of fkj also scales epsilon. Okay, let's summary. I'll do a summary. So our paper yields the first unified theory for identifiability and estimation in this model without requiring a linear independence condition or any parametric assumptions. So the estimation of the component distribution is robust under incoherence, and we have an algorithm to actually do that. Okay, so for more details, you can see our paper on arXiv, and that's all today. Thank you for your attention.
Yeah, so let's thank the speaker again. Yeah, so I think we have some time for one short question. Anyone in the audience? Okay, so you mentioned the correctness of the algorithm, right?
Yeah.
But like I think computationally, any
it is an efficient algorithm. It can be computed in polynomial time.
But like with not so high powers of polynomials, you mean, or? Because I think it was quite hard to get the algorithm from.
Yeah, sure. I'm actually not going into details of this. So I'm sorry. What's your question again?
Yeah, it's just like the type complexity. So you're saying that it's polynomial, but yeah, so you don't know the powers of this.
Yeah, this is actually a little drawback from our paper now, and we are considering to make it
efficient.
Yeah, maybe more efficient. Yeah.
Okay. Yeah. Thank you. Yeah. Let's thank the speaker again. And yeah, the last talk at this conference, at least in this room. Yeah, it's called The Sample Complexity of Simple Binary Hypothesis Testing, Tight Bounds with Sequential Interactivity and Information Constraints, please.
Yeah, so I'd be really appreciated if everyone can stay awake for more 10 minutes. So yeah, I'm going to talk about the distributed hypothesis testing. This is a joint work with Ankit Pensia and Varun Jog. So let's start with the simple binary hypothesis testing. In this setting, we have a hidden parameter theta, which in the Bayesian regime has a prior like Bernoulli of pi. And then we get n IID samples, x1 up to xn, from either p0 or p1. And that algorithm is going to decide between these two hypotheses. So the error would be just the probability that theta is not equal to our estimate. And we also define something here that would be useful in the next slides. So we define the optimal achievable Bayes error to be e pi between p0 and p1 by just using one sample from either distributions. So let's get into the distributed hypothesis testing. So up to the generation of the samples, it's the same setting, but then we actually assume that each sample is going to be observed by one sensor, but by different sensors. And then these sensors are going to send their information to a center, and the center is going to decide about the hypothesis. So this transformation between sensors and the center is going to be through some channels. So we define a set of convex channels to be our information constraints. So these channels that the sensor use should lie in this set of convex channels, set of convex channels. And so two important examples would be one that you can assume that each sensor, for example, can only use 2 bits of information to send to the center. So it would be communication constraint channels that are channels that have output size less than equal some parameter d. And the other example would be privacy constraint, that you assume that all these channels are epsilon differentially private channels. So, but for choosing these channels, we have some options. The simplest thing that we can do is to just choose one channel and use it for all sensors. So we call this setting identical channel settings. And we show the sample complexity of this problem to be n star ID. Sample complexity is just the minimum number of samples we need to achieve error less than equal delta in this setting. The other option would be to let sensors have different channels. So sensor 1 up to sensor n can have T1 up to Tn. And the sample complexity of this setting is going to be denoted by n star non-IID, sorry. And the last setting is sequentially adaptive setting, which we allow sensors to interact with each other. So the first sensor chooses some channel. The second sensor can observe the output of the first sensor and chooses its channel based on that output. The third sensor can observe Y1 and Y2, the output of previous channels, and chooses its channel based on these outputs. And we denote the sample complexity of this setting by n-star sequential. So we are going to answer two important questions about this model. The first question is the role of interaction. Does really the sequentially interactive setting help us to reduce the sample complexity in a non-trivial way? So does n-star sequential, is n-star sequential significantly lower than n-star non-IAD or not? First of all, I should mention that this question actually makes sense because there are some works on other statistical problems that shows that sequential interactivity can actually help to reduce sample complexity in a non-trivial way. And a prior work by Pensia et al. Shows that the sample complexity when we allow channels to be different is within the constant factors of the sample complexity when all the channels are the same. But they didn't study the sequential interactive setting. The second question that we are going to answer is about the sample complexity when we have communication constraints. So how does this sample complexity behave with our communication budget D? So if we denote the sample complexity of the hypothesis testing, a simple hypothesis testing without any constraint to be n-star, a prior work by Pensia et al., 2020, these are two works, 23 and 24, they show that in a simple setting when our desired error is some constant fraction of the prior pi, they show that n-star ID is upper bounded by n-star times logarithm of n-star over pi over the communication budget. And they also conjectured that 1 over pi should be able to be removed from the inside of the logarithm. So regarding the first question, we actually show that in a very general setting, sequential interaction doesn't help. So we show that sample complexity n-star sequential is lower bounded by 1/4 time n-star ID when we use just one, when we use the same channel for all the sensors. We use this technical tool to prove this result. We call it one-shot lower bound on the optimal Bayes error. So let's define beta lambda between P and Q to be Hellinger affinity, which is defined like this, for any lambda between 0 and 1. And then this is a known fact that the optimal Bayes error between two distributions P and Q is upper bounded by some function of pi, which is prior, and lambda times beta Hellinger between these two distributions. So we actually show that for some specific choice of lambda, this upper bound is tight. So we show this result that for some lambda star, we have this lower bound. And something to note about this lower bound is that beta lambda tensorizes easily, so it makes this lower bound useful for the sample complexity problems. Regarding the second question, we actually characterize the sample complexity of communication constraint hypothesis testing exactly. So we show that the sample complexity is actually upper bounded by n-star times logarithm of n-star over the communication budget. So something to note is that it shows actually that communication constraint doesn't add that much sample complexity, so it's just multiplicative factor of logarithm of sample complexity. And we use the technical tool, which can be of independent interest to prove this theorem. We call it reverse data processing inequality. So we all know that if we input two distributions to a channel, then the output distributions will be closer in sense of F divergence between them for any of F divergence. we actually show that for a fairly general kind of F divergences and for communication constraint channels, there always exists a channel T star that we have a lower bound on this F divergence between distributions, so we can preserve some information. So for summary, we showed that sequential interactivity actually does not help in the hypothesis testing, in information constraint hypothesis testing. And we also showed that communication constraints are benign. So one open question to pose here is that if the fully adaptive version of this problem actually help to reduce the sample complexity or not. By fully adaptive, I mean we have some rounds of communication. So in the first round, we have sequential adaptivity. In the second round, we observe all the previous outputs. And again, we have sequential adaptivity and so on. So thank you for your attention.
Thank you. So, unique chance to ask the last question in this conference. Anyone? Yep. So you mentioned these new technical tools, and I heard from colleagues that it's actually like it has some applications even outside like of your paper. Could you please maybe comment a little bit more about this reverse?
Okay, so I have some more slides here. So this is our one-shot lower bound. One application is just proving sequential interactivity does not help. The other
using your
application
new data processing, you mean?
You mean data processing quality, lower bound?
Oh yeah, that's one.
Okay, other applications, you mean
no,
outside
I think this is an extra slide, right? Because you didn't write
this
it.
is a new slide, like
okay,
after
I see.
the, yeah. So
yeah, maybe this was my question.
So this is the exact lower bound that we proved.
Mm-hmm. Okay.
Yeah. And TV-like F divergence, I mean, the F divergences that are bounded up to some point and after that behave like linear, so like TV. Or Hellinger distances are also F divergences, TV-like F divergences. Yeah.
Okay, any other questions? Okay, yeah, so I think there are many people whom we should thank now. Let's first thank our speaker again. Yeah, and then I think it's, at least for this session, we also need to, at least from my side, we need to thank the organizers and those who helped to organize these sessions and all the previous sessions. Yeah, I think are there any closing words planned here at the conference? I'm not sure about that. But yeah, in any case, let's thank everyone again.